Today my plan is to cover two or three things, depending on how you want to break it down. I want to talk a little more in detail about the nature of conjugated dienes in terms of their structure. I also want to talk about the reactivity of conjugated dienes, which is special due to the special nature of their structure. And then I also want to get into why it is that you get multiple possible products. Did I start Reef? I think so. Wait, or am I still on my other class? Let me see. Guess I do have to end the previous class. So you guys are starting now. So yes, thank you. Please do register your attendance. I do also have a Reef polling session today. I've got 2 questions for you guys. But out of the 100 points, 80 will be attendance. So certainly, please register your attendance. I'm going to use that to take kind of a break when we're done talking about the reactivity of these things. Do you record and post these lectures? Yes, I'm recording this one right now. Actually, I have to because I forgot to record the previous class. So I mean the previous section to yours. That at least gives me a choice of 2 different lectures, and I can put up the one that I think is better. So it's this one for better or worse. If it should ever happen that, God forbid, I forget to record both lectures, well, then I'll make a separate lecture. That will be my punishment, is I'll make a separate lecture and post it on YouTube. Now, do you all have my, yeah, you have, that's my YouTube channel. It's called R86 Chemistry, for reasons that would utterly bore you, but have some historical significance in my personal life. But yeah, so if you subscribe there, I'm totally fishing for subscriptions here, but at least you'll get the notifications when it's updated. Yep, and I should also mention, once we're about halfway done through the term, you'll also have at your disposal all of my lectures from last year. So it'll be the same material. I don't think there'll be too much difference. Good. So today we're going to get a little bit into conjugated dienes. We're going to spend really 2 lectures on conjugated dienes and their reactivity, which again is somewhat special, before we go on to consider aromatic compounds, which all we currently know officially is that benzene and aromatic compounds are not alkenes. And so they do not behave at all like alkenes. What they actually are and what they actually do, that's what we'll get to in chapters 15 and 16. Good, so just to start out with an example of a conjugated diene, I could have picked any conjugated diene. I picked 1,3-butadiene because it's the simplest one. But of course, you can replace any or all of these hydrogens and those carbons with other alkyl groups, and you'll still get a conjugated diene. And I should mention up front, these don't even all have to be all 4 carbon atoms. You could have other atoms here and you still would have a conjugated system. For instance, if you replaced this CH2 over here with an oxygen, you'd get an aldehyde that happens to be called a chrolene. I don't really care if you know that, but that would also be a conjugated compound. And so anything we say about butadiene would also be true for a chrolene. So here's the issue. This structure here, which we really would have no choice but to draw. I also realized my S-trans conformation went away. So let me just draw that in there. But these structures, like we're drawing them here, are what we would consider to be the structure of butadiene using the valence bond model. But butadiene and other conjugated dienes and other conjugated systems have something going on with their structure that means it's one of those times, goodness knows we avoid them, but it's one of those times where we have to think about molecular orbital theory at least a little bit. And I'm no big lover of molecular orbital theory either, but there's some times that we simply have no choice. We have to think about it. For instance, when we're looking at a species that exhibits resonance, we still draw valence bond structures, meaning that we treat these as localized double and single bonds. But there's something going on here that that means, let me call up our class notes. Here they are. There's something going on here that cannot be explained by the ordinary valence bond model. So conjugated dienes and other similar conjugated systems are special. I think I'm going to have to leave that as larger for the time being. Good. And what is that special thing? Well, I could put it in the most simple, straightforward way by saying the one thing that jumps out at us immediately is that this double bond, this single bond in between the two conjugated double bonds is very much shorter than theory would otherwise predict. If you had localized double bonds and a localized single bond. And then another part of it actually is that there's two conformations of 1,3-butadiene that are especially preferred over all the other possibilities. And I'm mentioning this now because we'll use this idea on Friday, the idea of the S-cis and S-trans conformations. They're terrible names, very, very confusing. But those are the names of these two conformations, these two favored conformations of 1,3-butadiene. Again, you could come up with similar conformations for any other conjugated diene or conjugated system. The S in S-cis and S-trans stands for single bond, which you'll immediately recognize is bogus. You can't be cis or trans around a single bond. By definition, it's something we use only for double bonds. But we're breaking the rules here and using it for single bonds anyway. And in the case of the S-cis conformation, we're saying that those two CH2s are as if they were cis to one another, even though it's around a single bond. Here it's as if they were trans to one another. So I've come up with another way of describing it that in my experience makes a lot more sense, both to students and to myself also. You can also think of whenever you see S-cis, you can think to yourself, or you can in your mind replace it with the word eclipsed. So by conjugated, we defined conjugated double bonds in one of the earlier classes. Conjugated means that you've got two double bonds, and they don't have to be between carbons, but they're separated by exactly one single bond. So that definition is in the other part of the class notes of chapter 14. And what we're saying about conjugated double bonds is there's two particularly favored conformations, and these are they. So in one of them, the two CH2s here are eclipsed. So I'm using eclipsed with the same definition as we gave back in chapters 2 and 3, way back in Organic 1. And in the S-trans conformation, those two atoms are perfectly staggered. They're exactly 180 degrees apart. So if you find those terms S-cis and S-trans confusing, which I don't blame you at all if you do, whenever you see S-cis, replace it with eclipsed, and whenever you see S-trans, replace it with staggered. And I think it will make some more sense to you. So if we're just drawing the structure of 1,3-butadiene, we're probably going to use a structure something like one of these two, even though that single bond in between the two conjugated double bonds is especially short. That can only be explained fully by molecular orbital theory. And so what's going on instead is something like you see in these structures here. Really, those 4 electrons in the 2 pi bonds are not localized. Really, they're somehow spread out over the entire molecule. And again, it's kind of hard to show that. We might need to do something like this. But we do need to bear in mind, at least stick in the back of our mind, when we're dealing with conjugated dienes or other conjugated systems. Doesn't have to be a diene. I gave the example of a acrolein earlier. But we do need to bear in mind that even though we might draw it like this, we really kind of have no choice if we want to be clear at all. We need to keep in the back of our mind that really those 2 double bonds are not localized, and neither are the 4 electrons that are in those 2 double bonds. That's the way we need to think about conjugated systems. in order to make sense of it. And so that was one thing I wanted to be sure to cover today. The other thing is the consequence of all this in terms of the reactivity of conjugated dienes. And what we find is that, well, first of all, to no one's surprise, I hope, conjugated dienes will undergo the same types of electrophilic additions that we learned way back in chapter 7 and 8. So we learned a bunch of reactions in those chapters, and all conjugated dienes will undergo the same reactions. I should mention, by the way, but I don't want to forget to mention that this chapter reviews some ways of making conjugated dienes, which is perfectly appropriate since that's what this chapter is about. Certainly fair to consider how we make these things. And we already know how to do that largely. We learned how to do that by elimination reactions, such as we covered in chapter 11. So as you know, in cases like this, I'm not going to reteach the organic 1 material, but I do my best. I'm sure I've missed a few of them, but I do my best to at least refer you back to where you can review that material in the textbook if you've forgotten about it. Not to mention, if you like, you can also even go as far as looking up my organic 1 videos on YouTube. They're all there if you would find that helpful to review this material. Good. So all of this, that before we get into the reactivity, all of this is to say that conjugated double bonds are more stable than isolated double bonds. And each instance of a double bond conjugation, which again, they don't have to both be carbon-carbon double bonds. It can be conjugated double bonds between any atoms. And I really don't care if you memorize this number, but each instance of a double bond conjugation wins us about 15 kilojoules per mole in stability, which is not a huge amount. You know, we're not talking about enough energy to break a bond. Those are in the hundreds of kilojoules per mole. But it's not nothing either. It's enough to make a difference. And it's enough to explain the short single bond between the two conjugated double bonds in a compound like butadiene. It's also enough to explain why it is that we get different reactivity of conjugated dienes as compared to just alkenes, isolated double bonds by themselves. And what we notice at first is that certainly conjugated dienes like butadiene will undergo electrophilic addition. And the only complication is there's multiple possible products. And I don't even just mean stereoisomers. There's multiple regioisomers that are possible. So, for example, if we treated 1,3-butadiene with, let's say, HCl, I'm just using HCl as an example. I could just as easily have picked HBr or HI. Well, one of the products would be exactly what we would predict. You would get the Markovnikov product of addition of HCl across a double bond. And in this case, technically speaking, you do generate a chiral carbon. So we would get both enantiomers. We'd get the R and S compounds both out of that. But that's only one possible of the two possible regiochemistries. And the other one, rather than the hydrogen and chlorine going on adjacent carbons, by the way, I should mention, the hydrogen of the HCl went onto this carbon, of course. You could draw that if you like, right? You can draw the CH bond if you want to. It's just you don't have to if you're using line angle drawings. It's understood. But this carbon's now a CH3, of course. Two of those hydrogens were there to begin with. The other one we got from HCl. So the chlorine we would expect to go on the more substituted carbon, coming from the more substituted of two possible carbocations. And so we would expect that would be one of our products. And this is called the 1,2 product. The 1 and 2 here, I'll get to the squiggles. The 1 and 2 here, but thanks for reminding me, are not exact IUPAC type numbers. They're just relative numbers. They're just saying that the hydrogen and the chlorine in this case, or the two atoms in question, go on to adjacent atoms. But there's also a 1,4 product where the, in this case, the halogen and the hydrogen go on to carbons that are 1 and 4 relative to each other. So that's another product that we get, and that's a different compound than this one, even accounting for stereoisomers. So it's typical with conjugated dienes that you get both possibilities, that you get 1,2 products and you get 1,4 products. Now, the squiggles mean, and you'll see that abbreviation sometimes. Here the squiggle, basically squiggle means mixture of both possibilities. Squiggle means mixture of both possibilities. Over here, the squiggle means that we'll get some of the isomer with the wedge bond and some of the stereoisomer with the dotted bond. In fact, I would bet that you would get a racemic mixture. So any question that you see either in OWL or on the exam will make it clear what you have to show. But if you ever see that, that abbreviation, that's what that means. The squiggle means mixture of both possibilities. Now over here, these carbons are not chiral. So here the squiggle means a mixture of both cis and trans, or of both E and Z. And indeed, I would expect you would get both. I don't know that you'd get 50-50 necessarily. I bet if any of us were to give a wild guess, we would guess that the trans compound will be more stable. And I would be shocked to find otherwise. But even discounting stereochemistry for a moment, you still get two different regioisomers. You get the 1,2 product and you get the 1,4 product. And it's typical with dienes that something like that will happen. We don't even need to use HCl or HBr or HI. And here I've even used a different conjugated diene. I've used cyclopentadiene. If we were to treat this with bromine, of course, I mean one equivalent of bromine here, one equivalent of HCl over here. Naturally, if we added an excess of HCl, you'd lose both double bonds. So here also just one equivalent of bromine. Well, we would expect still to get the 1,2 product, which would look like this. And in fact, you'd also get the enantiomer of this compound. Instead of down-up, you'd get up-down. So do review about stereochemistry of these additions. You still have to know that. That was part of the Chapter 8 material. And in this case also, you'd get the 1,4 product, which would look something like this. Here, the two bromines that we added are in a 1,4 position relative to each other. So again, these are not the same numbers we'd use like for naming alkanes. They just are expressing relative positions. 1,2 meaning that they're next to each other, 1,4 meaning a relative 1,4 position. And so, and I realize this compound's also chiral, so you would also get the enantiomer of this. Again, the question will make it clear what you need to show. Sometimes OWL even says, don't worry about stereochemistry. So they will tell you what you need to do to get credit. You just have to read the directions carefully. But that leads to the question then, why? Why are we suddenly getting, even discounting stereochemistry, why are we getting 2 products where we only can expect 1? Wouldn't the second bromine product be? Yep, that is the 1,4 product. Yep, this is 1,2 and this is 1,4. And the reason is we just count 1, 2, 3, 4 for the two carbons that bear the bromines. Yep. So you'll in general expect to see a 1,2 product and a 1,4 product. Whichever of those Chapter 7, Chapter 8 reactions you use on whichever conjugated diene you use. In general, you'll expect to see a 1,2 product and a 1,4 product. It was at this point, and I'm sure a lot of you are wondering the same thing, but someone in my previous class asked, well, which predominates? Excellent question, we'll get there. That's about 3 or 4 steps ahead of where we are now, but we will get there by the end of class today. So that leaves the question, why didn't you count clockwise for the second bromine product? Because this carbon, the CH2 carbon, is not involved in the reaction. It doesn't exist. Bella's yelling at me. It doesn't exist in the butadiene. So that's why you count from 1 to 4 this way. The reason we do that is to make this diene look like this diene in terms of nomenclature. So no, we don't call that the 1,3 product. We call it the 1,4 product. This CH2 isn't involved in the reaction. It's only these 4 carbons that are involved. And there will always be 4 of them like that, with no exceptions. So you'll always have a 1,2 product and a 1,4 product. Makes sense? Make sense? Which leads up to the question, why? Why do we get 2 products? And the reason is because, as it turns out, the carbocation intermediate that we get in this reaction, again, please review from chapter 8 if you've forgotten about these carbocation intermediates. But this is no ordinary carbocation. This is a resonance stabilized carbocation. The mechanism to give the 1,2 product is very straightforward, exactly what you would have guessed. If I'd asked this in an exam last term, I very well might have, for all I know, I don't remember. But I would expect anyone to get that mechanism correct. We simply protonate one of the double bonds, doesn't matter which, they're the same. Markovnikov's rule says we will get the more stable of 2 possible carbocations over here as opposed to over here, since you have a more substituted carbocation. And then our chloride ion, I seem to have lost my chloride ion. Our chloride ion attacks that carbocation like that, and we get our product. We get a mixture of the wedge bond and the dotted bond. And in fact, I see no reason why we would not get a racemic mixture. Do you mind? Bella's here smelling my class notes. Do you mind? Oh, I'm kidding. Anyways, poor old Bella. Never enough attention. Never enough admiration. Anyway, so that's how we would show the mechanism that gets us to the 1,2 product. What about the 1,4 product? Well, there's a couple different ways to consider it. The first step is the same for both of them. It's protonating that double bond, and then we need to bear in mind that this carbocation is resonance stabilized. There's also a resonance contributor that has some plus charge on this carbon. Even though that carbon is primary, because we have a resonance stabilized carbocation. Remember also, this is not an equilibrium, right? We're just doing resonance in my 227 class now, and I told them I have to remind myself to this day, so let's all remember, this is for my benefit too, this is not an equilibrium, it's not flipping back and forth. What it means is that there's some plus charge on this carbon and also some plus charge on that carbon. And so certainly, you could have the halide ion add to that carbon. And so that's how you would show the mechanism for that other one. By the way, quick review, you'll notice that I unhesitatingly drew that bond just as a straight line, and I didn't worry about wedges and dash bonds. Why did I know that I could do that? Why did I know that that was okay? Something about this carbon.
It's not a chiral center?
Not chiral, right. Yep, 2 hydrogens, not a chiral carbon. So not an issue. So that's the sort of thing that I will expect you guys to be comfortable with. So where was I? And you would also get the, let me get this right now, the Z isomer as well, right? This one is E for antigagon because they're across from one another. That's not the only correct way to draw that mechanistic step. In case you're curious, this is something I generally find a lot of students are curious about. There's another way you could show that that's perfectly acceptable. Let me just sort of excise the cyclopentadiene one from here so I can make a little bit more room. And it's just by nature of that being a resonance stabilized carbocation. So another perfectly acceptable way to show it, let me just sort of steal this resonance form. Since again, the first step of the reaction is the same for both of them. But another thing you could do to show how you get to this structure that's absolutely 100% acceptable is you can show the halide ion attacking that terminal carbon. Then you just need one more arrow to show the double bond, whoops, other kind of arrow. There we go. You just need one more arrow, show your pi bond shifting in to form a pi bond between the other 2 carbons, and that is also perfectly acceptable. That gets you straight there also. Not only would I not take off points, I would just immediately assess that it's the same thing and move on. So you can do it either way, by showing the other resonance form or by something like this. In case you're curious, this type of step is sometimes called an SN2 prime type step. So it's like SN2 with an extra bit. But be that as it may, either way is completely fine. So, so that explains mechanistically as to why we get these two products. It turns out then that these two products are not created equal. We got to get to this issue of which of those predominates. And so I'd like to go over that for a little while, and then I'd like to do our brief session, and then we'll end up with our grand finale will be the energy diagram for this whole mess. You're going to be so jealous when we get to things like carbohydrates and proteins. I can draw like entire amino acid molecules with one mouse click. Here, I'll show you. Let's see. Amino acids. Did you ever figure out your labs in determine office hours? I'm glad you asked that. Answer is no. And the reason is, from my understanding, you can correct me if I'm wrong, but from my understanding, all of, let's see, this is going to be arginine. There you go. There's your arginine. Anyway, enough showing off. Or how you young people say, enough flexing. But my understanding is this week's labs are all online. And so they haven't told me my schedule yet. I'm still pretty sure to date, they've always given me a Wednesday evening lab. I don't know when the other two will be, but you may be flexing too hard, yeah. But you may be certain that the very second I know my schedule, I will immediately go and figure out when my in-person office hours will be, and you guys will know as well. I was expecting them to tell me by last Friday. Actually, just yesterday, I texted Dr. Pennington. I'm like, do we know when our labs are yet? He said, well, you got the email that they're online this week. So, oh, yeah, right. So that's the situation. I am always planning on being around before this class and before my section 513 as well. And also, I'll get there a little early for my Chem 227 classes, which start at 11:30 on Tuesday, Thursday. They're 11:30 to 12:45. So, you know, by 11:10, 11:15, the latest, I should be around there too. But I do plan on having in-person office hours whenever I need to be around anyway in my office for labs. Good. So let's compare these two types of products. Other things that we know about the 1,2 product. In this case, this is also called the kinetic product. And this is not the only case we'll run into where you have a choice between kinetic and thermodynamic products. This issue of kinetic versus thermodynamic control is something we'll run into a few other times at least the rest of this term. So this is not the only case. It's not rare. It doesn't happen for every reaction, of course. There are some reactions where both the potential product that's more stable is also the one that's formed more quickly. So there's not an issue. You just get one product. But sometimes you get a divergence between the two. This is one of them. Another thing we can say about the kinetic product is that it is the one that's less stable. That's always going to be the case. And another thing we can say about the 1,2 product is that it's favored at low temperatures. And we'll say in a moment what exactly we mean by low, or not exactly, what roughly we mean by low temperatures. The 1,4 product we also call the thermodynamic product. I'm just going to go prod since I'm running out of space. The thermodynamic product is always going to be the one that's more stable, other things being equal, than the other product. This is also going to be the product that's going to be favored at higher temperatures. So not all kinetic products are 1,2 products. You know, that the 1,2 and 1,4 products are just the names, respectively, of the kinetic and thermodynamic product for this particular type of reaction. But we will run into other cases of kinetic versus the thermodynamic control. And your kinetic product is always going to be your one that's less stable. Oh, I missed one, didn't I? All these are true, but I forgot to say also that the kinetic product is formed more quickly. And the thermodynamic product is going to be the one that's formed more slowly. Yep, we have to have that in there as well. So again, what we're saying here is we only call the kinetic product the 1,2 product in the case of this type of electrophilic addition to dienes, and the thermodynamic product the 1,4 product in this particular case. But there are other reactions that have this issue. And in those cases, in addition to in this case, the kinetic product will always be the less stable one. The thermodynamic product will always be the more stable one. Always, no exceptions. The kinetic product is always going to be the one formed more quickly. The thermodynamic product, the one formed more slowly. Again, always, no exceptions. And again, the kinetic product is the one favored at lower temperatures, other things being equal. The thermodynamic product favored at higher temperatures. Do 1, 2, and 1,4 products only occur in dienes? Oh, there might be something else where you wind up just by chance using that nomenclature. I don't know if we'll ever run into any of them. But what I would say is the kinetic product is only called the 1,2 product in the case of this type of reaction involving dienes, at least for us for right now. I don't know if we'll run into any other ones. The thermodynamic product is only called the 1,4 product for a reaction of this type. But there's other possibilities of kinetic versus thermodynamic products that might be called other things, if that's what you mean. But all these characteristics of the kinetic product will always be true. All these characteristics of the thermodynamic product will always be true, no exceptions. One other thing I want to cover here, which again, I know a lot of you are going to be wondering, and very reasonably so. What do you mean by low temperatures? What do you mean by high temperatures? And of course, that depends on the type of reaction. Now, you'll notice when you're reading the book, they will bring out like exact temperatures and also exact particular percentages of the 1,2 and 1,4 products. Of course, I would never expect you to memorize any of those, nor to speculate on exact numbers like that. Even if it were an open book, I would never expect you guys to memorize things like that. But if you want sort of a rule of thumb, at least for this type of reaction, I've generally noticed that the cutoff point is probably somewhere around and about room temperature. As you know, room temperature is generally in the mid-20s. How do we know if it's a kinetic or thermodynamic product? Well, if you don't know anything about the reaction, you can't possibly know. Here, we know that we know from experimental results that that this one is both less stable and formed more quickly, and this one is both more stable and formed more slowly. But if you're just given something you've never seen before, you can't possibly know, at least not a way that I can think of. I mean, you might be able to make a good guess. Can you see a reason maybe? I mean, to answer your question, how can you know for 100% sure? I don't know that you can. Can you make a good guess? I think you can. Anyone see a reason why this compound might be less stable than that one? Hint, look at where the double bond is. And I think you'll be able to come up with a way to convince yourselves that this is indeed the less stable product, that one is indeed the more stable product. Less stable will always be kinetic, always, no exceptions. More stable, always thermodynamic, no exceptions. Terminal double bonds, yes, this double bond is only monosubstituted. This one is di-substituted. And in chapter 7 last term, we said that other things being equal, more substitution is better. More centralized electron density, sure, you can put it that way too. Another perfectly correct way of saying the same thing. Maybe because the double bond, the chlorine are cis to each other, so there is, oh, well, but no, because you have full freedom of rotation around this single bond. So it's a question of the chlorine over the methyl. Actually, I would expect the chlorine would take up less space than the methyl. But the same cis-trans stability and conjugated dienes apply that we saw in alkenes. Remember, we went over that silly S-cis and S-trans stuff. Now, if you're talking about each of the double bonds by themselves, can you have E and Z isomers and will the usual stability rules apply? Yes, absolutely. But if you're talking about the two relative to one another, then refer back to the S-cis and S-trans, or if you will, eclipsed versus staggered stuff that we covered earlier. So anyway, briefly on the temperatures issue. So I would say if you're given a temperature, if you're given a reaction like this, and you're given a temperature that is significantly below room temperature being generally in the mid-20s Celsius, that's usually a nice, comfortable temperature in the low to mid-70s Fahrenheit, something like that. You can figure it out on your own. Usually in that case, that's going to be a low temperature. I'll get your question in just a second. And if you see something significantly higher than room temperature, if you're given 40, 50, 60 degrees, probably you're under thermodynamic conditions. I wouldn't be shocked, I don't remember for sure, but I wouldn't be shocked if you looked at my old exam and I would write low temp or high temp. Sometimes I just do that. I meant like how an alkene, a transalkene is more stable than cis, so the S trans conjugated more stable than S. Oh, I see what you mean. I think they're actually pretty close. I wouldn't be surprised though if you're right. I just don't know the numbers right off the top of my head. But yeah, you would expect that the S-trans, so-called S-trans conformation would be more stable. I expect you're probably right in general. I mean, you can mess it up by putting other groups on here for sure. We will actually see one such example. But if you're just talking about unsubstituted butadiene, that would be my expectation too. I would expect you're right. Good. So from here, I think we can clarify all this by going to the energy diagram. I want, though, to leave that for after our reef session. I want to take a little break from all of this first. So hopefully you've all registered your attendance. I'm going to switch over to polling. And here's our thing. So we'll start the slideshow. So, and again, 80 of the 100 points for the day is just for attendance. So question 1, this relates to what we talked about last time, which was on mass spectrometry, which is, and I'll start this in just a second, which of the following fragments would you not expect to see evidence of in the mass spectrum of dibutyl ether? And I've given you the structure of dibutyl ether just in case. So I would put it to you that of those 5 fragments, 4 of them are ones we might reasonably expect to see in the mass spectrum. Maybe we would, maybe we wouldn't, but it would be reasonable to expect. And the 5th one, there's no way, we would not expect to see that one. At least there's no clear and obvious way as to why that would be there. Do you have a cat mansion or house thing? Not really. Actually, I did for a little while. 30 more seconds, please. What do you call it? The shelter that I adopted Barnaby from gave me one, and I put it out there, and they both ignored it entirely, so I let them take it back. They had a bunch of kittens who I know would have just loved it. Was added in your class about 30 minutes before this session started. Will this recession count against me? Put a shoe on. Yeah, or a paper bag, that always works. If you've added it into the class, then it will probably work. So we can wait and see. Yeah, if you've added into my reef section, then it should be fine. Okay, so that's enough time. Well, remember that the criterion you should use, second last, oh no. That's true, it's kind of surprising they're not sitting on the laptop. Anyways, remember the criterion we used was, at least as a first approximation, certainly starting for the easiest cases, you want to take fragments that are pieces of the molecule. And can we get a CH3 plus? Sure we can. We can get one off the end over here or one off the end over there. So would we actually see CH3 plus at 15? Maybe, maybe not, but we could reasonably expect to. What about propylcation? Well, sure, there's a propyl group over here, propyl group over here. Same thing with the butyl groups. There's certainly a butyl group. Butyl oxycation, sure, you can break the bond over here. and get this fragment. And there's certainly others we could maybe get also. But this one here, the CH3O plus, I don't see a CH3 attached to an oxygen anywhere. So I don't see a good way that we could get that fragment. It would be some really weird rearrangement of some kind. So I think A is the best answer, as did you guys. Good. And my second and final question concerns something we will cover on Friday, but I've given you all the information in this question that you need to know to figure it out. So on Friday, we'll learn about the Diels-Alder reaction, which works with conjugated dienes in the S-cis conformation. Which of the following would not be a good starting material for this reaction? And I would put it to you that 4 of those would be perfectly good choices. The 5th one, not so much. You can always see your reef. Yes, but I do want to warn you guys all again, any grades that it gives you on the Reef app are going to be wrong. I'll try to massage it a little bit and see if I can get it a little better, but they're going to be wrong. In particular, you'll probably see be given a whole bunch of zeros that you didn't actually earn. I've heard, for example, that you would get a 0 for the Reef pulling session we just did in section 513. Well, of course you will. You're not in that class. Or if we do one in my 227 class, you're not in that class. So that 0 won't count. So I always need to download the data and massage it and figure out what exactly they meant so that everyone gets the correct grades. It's something that needs to be done by human eyes, it seems. So I will always upload, as soon as possible, your Reef grades onto eCampus, and anything you see on eCampus will supersede whatever you see on the Reef app. And hint, by the way, what you see on the Reef app will probably be, extremely wrong and unfair. Okay, so we've taken enough time for that, I think. So I think there's 4 of these that are, the actual questions are there, and you can use the Reef app for that. But I mean, don't take any grades you see on the Reef app seriously. It's probably wrong. Wrong in the sense that it's probably less than what you actually have. Good, so what we'll say on Friday is the diene needs to be conjugated, and it needs to at least be able to adopt an S-cis conformation. And certainly A and D are great dienes because they're actually locked into S-cis. B is good also. This one here could, of course, also go S-trans, but it is able to adopt an S-cis conformation. So we're good. I would say A, B, D, and E are good choices. In C, this diene is not conjugated. So that one would not work, and I think that one's the best answer, as did you guys. Good, so let me go in here and just take like 2 seconds to put in the answers. We'll save that. And yes, I will be uploading that to eCampus probably as soon as today. Good, so there's just one more thing I want to go over in our waning 5 minutes, which is what the energy diagram would look like for this. And I think we can learn quite a bit from that, actually. And so what I've drawn here is the energy diagram of that second step. So I'm not starting at the starting material here. I'm starting at the intermediate, that allylic carbocation, which again is the same intermediate for both 1,2 and 1,4 products. And this diagram would look much like this for any conjugated diene undergoing any electrophilic addition. The starting material, of course, would be over here somewhere. And if we wanted to, we could show that going up through a transition state and ending on the allylic carbocation intermediate. That's fine. You could if you wanted to. But I'm just focusing on that second step here because the first step is the same for both the 1,2 and 1,4 products. So what we find in going to the kinetic product, again, remember we said the kinetic product is the one that's less stable, so it's higher in energy than the thermodynamic product. But we also said it's formed more quickly. So you'll notice the transition state going to the kinetic product is lower in energy than the transition state going to the thermodynamic product. Makes perfect sense. If you say that a reaction's faster, or is the faster of 2 reactions, that's just the same thing as saying that the transition state to the product is lower in energy than the other transition state. Or you could say you have to get over a lower energy barrier than for the other one. Those are just three ways of saying the exact same thing. The product is formed faster, its transition state is lower in energy, or you have to go over a lower energy barrier, lower activation barrier. There are just three different ways of saying the exact same thing. And likewise, the thermodynamic product, being more stable, will be lower in energy than the kinetic product, but its transition state will be higher in energy than the transition state going to the kinetic product. And this is always what you see for any type of situation where there's kinetic versus the thermodynamic control. So you'll always see something like this. You'll always get a kinetic product that's higher in energy but formed more quickly because you go through a lower energy transition state, versus the thermodynamic product that is more stable but is formed more slowly due to having to go over a higher energy barrier. And I only have 2 more minutes, but I think that's just about enough. That is why what we said before about the temperatures is true. We said that the kinetic product is going to be favored at low temperatures. That makes perfect sense, because at low temperatures, we don't have enough energy in the form of heat. We don't have enough thermal energy to get over that higher activation barrier. So, I mean, I guess it might happen a few times, but certainly you'd expect that in the majority of cases, we would, probably the vast majority, we'd go over the lower barrier since you have less thermal energy available, and you would tend to collect more of the kinetic product. Meanwhile, what if you have a higher temperature, more thermal energy? Well, be aware, of course, that doesn't mean that you can't go over the lower barrier. You certainly could. You certainly will get some of the kinetic product. But if there's more heat around, then there's enough energy to go back over the transition state and revert to the starting materials, and then have a second chance at getting over that higher barrier. So with more energy in the form of heat, we've got choices. We have enough energy to go over that higher barrier outright and get to the thermodynamic product, which we couldn't do at a lower temperature. And even if we do get some of the kinetic product, there's enough energy around for this product to revert to the starting material. Let me just finish this idea and then we'll cover what allylic means. Well, I'll just say allylic is defined in either chapter 10 or 11, but I gave the place that, oh, there you go, review 11.5. So that's where you would go to review the definition of allylic. But be that as it may, right, so you also have enough energy, even if you get any of the kinetic product, for this to go backwards and revert to the starting material, and then get another chance to go over that higher barrier. So no wonder this is temperature dependent. And I think this makes sense as to why lower temperatures favor the kinetic product and higher the thermodynamic, other things being equal. So essentially, added heat allows for equilibrium to be reached. Couldn't have said it any better myself. Exactly right. Whereas with lower temperatures, maybe not so much. You're only going to have enough energy in general to get over the lower barrier, and then you're kind of stuck. But at higher temperatures, you can achieve equilibrium. Yep. Good. And in fact, what you just said about equilibrium being reached, to say that the thermodynamic product is the one you get more of if the thing is allowed to achieve thermal equilibrium, you're just saying the same thing again. It's another perfectly correct way of saying the same thing. A little carbon is a carbon atom bonded to a carbon atom that is double bonded to another carbon atom. Sounds good. Something like that. Good. Well, I'm out of time. So that leaves us to cover the Diels-Alder reaction on Friday, which we should be able to do with no trouble. So other than that, unless there's any pressing questions, which is fine if there are, but other than that, we'll see you all on Friday.